Content-adaptive lenticular prints. Lenticular array prints are commonly used to produce automultiscopic displays. The full 4D light field emitted by these prints has a fixed spatial and angular support, which is defined by the lenses used and the number of pixels underneath them. However, a given input light field has locally varying angular and spatial frequency content. Thus, a regular lens pattern does not make best use of the input content. We analyze light fields to compute optimal lenslet shape, size, and arrangement to best match the content for given output print parameters. In this way, we are able to increase both angular and spatial resolution. Here we demonstrate this principle. This input light field is focused on the houses in this scene, which have low angular frequencies and sharp, high spatial frequency details. The background and train have high angular frequency content from the parallax caused by the motion of the capturing camera. Using a regular lens sampling strategy, we can choose either high spatial resolution on top or high angular resolution on bottom. In contrast, our approach produces variable spatial and angular resolution. The houses have high spatial resolution and the background and train have high angular resolution. In this example, the input light field is focused onto the face of the elephant. Regular samplings cannot capture both the high angular resolution of the background and trunk and the high spatial resolution of the face. Our approach captures both by optimally arranging lenses of different sizes and shapes across the display surface. By default, our approach produces an appropriate balance of spatial and angular resolution. Here we show a scene with specular reflection and refraction. The input light field has both high spatial and high angular frequencies in the same content within the crystal ball, and this is a challenge for our approach. With the same scene, we also show a comparison between a shallow and a deep input light field. Our lens simulation reproduces the content-adaptive light field well, as there is little visible difference from the pure synthetic case. This shows that, with good fabrication methods, our optimizations would generally perform well. High contrast, rounded edges may cause problems with our approach, and we highlight this here with two failure case scenes. Flickering can be seen at the edges of the red apple. Advances in 3D printing now allow the fabrication of near-optical quality materials. This enables direct printing of lenticular lenses with embedded display pixels, which solves alignment issues with separate lens and content sheets. 3D printing lenticulars allows new effects, such as printing baffles between lenses, or printing curved or faceted pixel display surfaces to improve focusing. For our optimized displays, 3D printing allows us to vary lens shape and size across the surface, as the display pixels need not be on a plane. Here, we show our prototype optimized prints of the train and elephant scenes. Areas of differing spatial and angular resolution are clearly visible. The trade-offs with this fabrication method are visually obvious. Lenses can only be accurately printed so small before the optical quality degrades, likewise with display pixels. This limits the output resolution of the display. Also, the number of materials available in any one print is small, here only 2, limiting us to grayscale output produced by varying the thickness of black material embedded within the lens array. If approximate color is sufficient, a simple trick can be applied to our grayscale prints. The color input light field is filtered according to the lens distribution, normalized in intensity, and positioned behind the lenticular print on an LCD display. This acts as a spatially varying colored backlight. The geometry of our prints is too complicated for our 3D printer's software to manage, being commonly 10 to 15 million triangles large. Hence, we have sliced the display into horizontal strips and joined them. Finally, we show more simulation results. Our optimized displays fare well in simulation against regularly sampled displays in both L2 and PSNR metrics. Furthermore, in a user study, our content-adaptive simulations were significantly preferred over the highest PSNR regular sampling case in 8 out of 10 scenes. Thank you for your attention.